Hello everyone, my name is Cintrum Dwi Widyaningsih. I'm from Dongso University and I will explain a paper entitled as Probabilistic Model Agnostic Meta-Learning by Chelsea Finn, Kelvin Su, and Sergey Levin from UC Berkeley. And this paper already presented and published in 32nd conference on neural information processing systems, or we can call it as NEUR IPS 2018 in Montreal, Canada. So the contents that I will explain to you in this presentation is begin with model agnostic meta-learning. I will just explain briefly about it, and then followed by the problem of MAML, so that the author of this paper have the new idea to make a proposed method called probabilistic model agnostic meta-learning, and then followed by graphical model, then probabilistic model agnostic machine learning approach with hybrid inference, then adding additional dependencies, the algorithm itself, the experiments, and the last is conclusion. So I will explain to you one after another in the next slide. I will begin with model agnostic meta-learning, or we can call it as MML. So basically the goal of the meta-learning itself is to train a model on a variety of learning tasks such that it can solve new learning tasks using only a small number of training samples. And based on that aim of meta-learning, the author of this memo make this algorithm so that our model can learn a new task by using a small number of data. So we can use our model to be applied to a few short learning. To do so, meta-learning algorithms or this MML require a set of tasks because we want to learn the task. And the formulation of the task in MML itself is defined like in the slide. You can see that because they want to generalize the this algorithm to reinforcement learning, they formulate the task as so that the tasks have the episode and the transition distribution, as you can see in the slide. Inside of the task, we will have the loss function that is calculated using the data that is denoted as x, and a is the action in the reinforcement learning, and we can just remove a when we want to apply MML in the regression or classification. And then what is h? H is the length of the episode. So if you want to apply MML to the supervised learning, we can just cut the x1, a1, x2, a2 until xh, ah to be just x1 or x1, a1 if you still need a1. Then we will have the distribution over the initial observations denoted as qx1 here. Then for the reinforcement learning, we may need the notation to explain to for the transition distribution, because we will always need the calculation when we want to move from the current state to the future state. And then if we want to, as I already explained, if we want to apply MML to the supervised learning or the other learning other than the reinforcement learning, we can just set the age as 1. So how can mammal learn the model by using a few short data? The answer is because inside of the mammal they have two optimization process. The first is the inner update and the second is the outer update. So based on the slide, the equation in the slide is basically the overall equation for the optimization inside the mammal. So if we can see the theta minus alpha and then multiplied by the differentiation of the loss function respect to the theta and the training data is basically the optimization inside of the inner loop. And then after we will do the inner loop for each task, for all the tasks that we want to learn. For example, if you have the 25 tasks, then you have to update your phi I using those equation, so that you will have 25 sets of phi I. Then after that, you apply your model again, your neural network again, to the testing data, and you will have, because you have 25 sets of the parameter, you will have 25 sets of loss value, and then you do the summation for all the loss function respect to the number of your tasks. So that's why in the sigma function, in the sigma operator, you have ti drawn from the distribution of t, because the summation is respect to the number of your tasks. And then you do the minimization respect to the theta, and then you can go to the outer loop and you do the optimization using the SGD or stochastic gradient descent, or the other optimization algorithm like a DAM and so on. The detail of the equation in the slide is the first one is the phi I, where the phi I is the parameter of a particular task, the parameter that is adapted from your particular task. So phi I basically is equal to theta minus alpha minus the differentiation of the loss function using your training data set. And then theta itself is your real parameter in your model. So we can say that phi I is just the temporary adapt parameter, but after and we calculate the phi I in the inner loop, and then after that, after we already got phi I, we will calculate the theta by using the adaptation or the optimization in the outer loop. So our real adapted parameter is basically theta. Then the L function is the loss function. If you apply mammal to the regression, you can use the MSE or mean square error as the loss function, or if you do the classification, you can just use cross entropy or using the error square like in the basic neural network that we usually use. Then alpha is the learning rate inside the inner loop. Then we will have another learning rate in the outer loop. Sometimes we call it as beta. And then the DTR and DTest is your training and testing set. If you want to know deeper about model agnostic meta learning, you can just check in the link below. So what is the problem of MML? Basically, in the recent days, there are more scalable approaches to few-shot learning that have focused on acquiring deterministic learning algorithms that disregard ambiguity over the underlying function. So basically, this problem is the local problem of MML itself. We know that in the MML we have the inner loop, and in the inner loop we do the adaptation over the several tasks. For example, 25 tasks. After the fast adaptation or after the inner loop itself, we will have 20 set of fast adapted parameters. So basically one set of this parameter is your weight in the neural network. So if we have 20 set of tasks, every particular weight has 25 value. So means that our particular weight has the ambiguity or the variance or our weight is not that deterministic. So if we look it deeper, we will have the some sets of distribution of our weights. So if we use, for example, if we have 200 weights, we will have 200 distribution of the particular weights inside of our model. So representing the distribution over the function itself is one of the solutions to overcome MML problem, because we will have the distribution over the weight. And these problems actually can be easily tackled if we just use the simple model like the linear regression or the other simple model, because we don't need too much or so much parameters. We just need maybe some parameters that is fit with our data. But if we use the neural network, and since our MML is applied to the few-shot learning, and it will be applied to the high dimensional data, the problem of this MML will be more challenging, because we have more approximators or the parameter prediction or the parameter estimation in our model. And to develop an approach that can tackle this problem, we have to make the method that has the benefits of scalability and the uncertainty. And because of that, the author built the variational inference for developing a probabilistic meta learning approach. So the proposed method is probabilistic model agnostic meta learning, and the goal of this proposed method is to build a meta learning method that can handle the uncertainty and ambiguity that occurs when learning from small amounts of data. And in this paper, their primary contribution is actually to reframe MAML as a graphical model inference problem, where the variational inference can provide us with a principled and natural mechanism for modeling the uncertainty and ambiguity. So, what is the variational inference? We will look at this in the next slide. So, the authors designed the hierarchical Bayesian for few-shot learning problem that includes random variables for the prior distribution over the function parameters, and it is denoted by theta, and then the distribution over the parameters for a particular task that is denoted as phi I, then the task training and testing data points. In the graphical model, we will have theta and phi, where those parameters are indexed by I. I is the index over the task. So, for example, if we have 25 tasks, we'll have 20 sets of theta and also 25 sets of phi. Instead of those parameters, we also have the training dataset and also the testing dataset. And if we see in the graph, the prediction for the y test is calculated from using phi I, where phi I is influenced by theta I or the prior, and also the evidence or the likelihood or the training dataset. So the posterior inference over phi I must take into account for both the evidence or the training set and the prior imposed by p theta and p phi I given theta. In the conventional MAML, actually we do the approximation of MAP or maximum a posteriori inference under a simplified model where the prior is the delta function. And we also do the inference that is performed by running gradient descent on log p of the target of our training dataset given the feature of our training dataset and also the fast adapted parameter phi I for a fixed number of iterations that are starting from phi I 0 or equal to the expectation of the theta. So the distribution p phi I given the theta can be approximated by Gaussian distribution with mean that depends on the step size and the number of the gradient steps. And then for the prior, if it is not deterministic, we have to make a further approximation to account for the random variable theta. One way that we can do to do the approximation is using the structured variational inference. And in this structured variational inference, we can approximate the distribution over the hidden variables theta and phi I for each task with some approximate distribution qi of theta and phi I. And there are two reasonable choices that we can make for qi of theta and phi I. The first is using the product of independence marginal according to qi. So we can just do the multiplication for qi of theta with the qi of phi I in this approximation. But this approximation does not permit the uncertainty to propagate effectively from theta to phi I. So we prefer to use the second approximation, that is the structured variational approximation. So in this approximation, we partition the qi to be qi of theta multiplied by qi of phi I given theta, where the detailed information of the notation in this slide can be seen in the bottom side of the slide. Since we know the method to approximate the distribution qi, now we can formulate the variational lower bound on the likelihood as in the slide. Then the prior p theta can be chosen to be Gaussian with a learned mean and covariance to provide for flexibility to choose the prior parameters. This corresponds to a Bayesian version of the Memel algorithm, and in this paper we will define this parameter as mu theta and sigma theta square. Then we have to choose the probability of phi I given the theta. One way to ensure a tractable likelihood is to use a Gaussian with mean theta, and basically this choice is reasonable because it can encourage phi I to stay close to the prior parameters phi. Then lastly, we have to choose a form for the inference network or the Q psi of phi I given theta or the Q psi of theta. They have to be chosen so that their entropies on the second line of the equation are tractable. Note that both of these distribution model very high dimensional random variables, and a deep neural network can have hundreds of thousands or millions parameters. So while we can use an arbitrary function approximators, we would like to find a scalable solution. One convenient solution is to allow the Q psi to reuse the learned mean of the prior mu theta. And the author observed that adapting the parameters with gradient descent is a good way to update them to a given training set and the testing set. And they propose an inference network of the form of the second equation. While this choice may at first seems arbitrary, there is a simple intuition. The inference network should produce a sample of theta that is close to the posterior. As a reasonable way to arrive at a value of theta close to this posterior is to adapt it to both the training set and the test set. And note that this is only done during the meta-training. It remains to choose the Q psi of phi I given the theta, which can also be formulated as the conditional Gaussian with mean given by applying gradient descent. Although this variational distribution is substantially more compact in the terms of parameters than a spread neural network, it only provides estimates of the posterior during meta-training. At meta-testing time, we must obtain the posterior P of Vi given the training dataset and the variable of the testing set without access to the target of the testing set. We can train a spread set of inference networks to perform this operation, potentially also using gradient descent within the inference network. However, these networks do not receive any gradient information during meta-training and may not work well in practice. To formulate a simpler variational meta-learning procedure, we recall the probabilistic interpretation of MAML. And basically, MAML can be interpreted as approximate inference for the posterior probability according to the equation in the slide, where we use the maximum posteriori or MAP value that is denoted by phi I star. And it can be shown that for likelihoods that are Gaussian in phi I, the gradient descent for a fixed number of iterations using the training dataset corresponds exactly to maximum posteriori inference under a Gaussian prior. In the case of non-Gaussian likelihoods, the equivalence is only locally approximate and the exact form of the prior P phi I given the theta is intractable. However, in practice, this implicit prior can actually be preferable to an explicit and simple Gaussian prior, since it incorporates the rich nonlinear structure of the neural network parameter manifold and produces good performance in practice. So after we know the approximate inference for the posterior probability, we can now formulate the approximation of the likelihood using the variational lower bound. As we can see in the second equation in the slide. In this bound, we essentially perform approximate inference via MAP on phi I to obtain the probability of phi I given the training data and the theta, and use the variational distribution for theta only. Note that Q psi is not conditioned on the training set of the theta is independent of it in the transform graphical model. Analogously, the previous section, the inference network, is given by the third equation in the slide. To evaluate the variational lower bound during the training process, we can use the following procedure. The first is we evaluate the mean by starting from mu theta and taking one or more gradient steps on log probability of the target test given the variable of the testing data and the theta of the current steps, where the theta of the current steps start at mu theta. Then add the noise with variance view Q, which is made differentiable via the reparameterization trick. Then take the additional gradient steps on the training likelihood log P Y training given the X training and the theta current. This accounts for the MAP inference procedure on phi I. The training of the mu theta, variance theta, and phi q is performed by backpropagating gradients through the entire procedure with respect to the variational lower bound, which includes a term for the likelihood loop, the P of y test given by the x test and the training data, and also the phi I star and the KL divergence between the sample of theta that is drawn from the distribution of q psi and the prior p theta. So basically the overall algorithm of the proposed method can be seen in the slide. The red written algorithm is the line that is different with the original memo. So in this algorithm, they initialize the big theta that contains the mu theta, variance theta, phi q, and the learning rate gamma p and gamma q. Then we do the sampling for the task that we want to train. Then before we do the evaluation for the model on the training data, we need to do the evaluation for the testing data first. So in the line 6, we will have the loss function using the testing dataset, and we can calculate the derivation over the loss function. Then we draw the theta using from the normal distribution that the mu is formulated using the equation in the line 7, and also using the covariance matrix phi q. Then we evaluate our model to the training dataset and calculate the loss function again, and also do the differentiation with respect to the theta. And right after that, in the line 9, we calculate the fast adaptation of the parameter or phi I, and then we will get the probability of theta given the training dataset that is following the normal distribution again using the mu value that is calculated by the equation in the line 10, and also the covariance is using the sigma theta square that we already initialize in the line 1. And then after this part, we go to the outer loop that we update the big theta, our real parameter. But before that, we have to calculate the equation over the summation of our loss value plus the value of the Kullback-Leibler divergence of our q theta given the testing data and the p theta given the training data. And then we do the optimization of our theta using the SGD or ADAM. And this is the result of the experiment for the regression on the toy data. So basically they give their proposed method name as platypus or probabilistic latent model for incorporating priors and uncertainty in few-shot learning. And if we compare the mean square error of mammal and platypus, we can see that the MSE of platypus is decreasing quickly than mammals. So it means that the result of platypus is much better than mammal in this regression experiment. And for the classification, they do the experiment of the platypus on the ambiguous expression dataset, and from the table we can see that the platypus almost covered twice as many tasks compared to mammal with comparable accuracy. And the mammal plus noise is a method that adds the noise to the gradient but does not perform variational inference. This improves coverage but results in lower accuracy average log likelihood. The conclusion of this paper is that the new algorithm for few-shot learning, so-called platypus, enables simple and effective sampling models for new tasks at metatest time. Then, this approach has number of benefits. The adaptation is exceedingly simple, and the method can be applied to any standard model architecture. And then the experimental results show that the method can be used to effectively sample diverse solutions to both regression and classification tasks at metatest time, including for task families that have multimodal task distribution. So that's all of my presentations. Thank you for your attention.